Good evening. My name is Rogelio Pumajulca, and this is the presentation for the paper Cross Miniapp Request Forgery, Root Causes, Attacks, and Vulnerability Detection. This paper presentation is part of the course INSE 6170 in the Master of Engineering Information System Security. To better comprehend this paper, we first need to describe some initial concepts. So, what is a super app? From the end user perspective, a super app is a mobile or a web application that can provide multiple services, including payment, financial transactions processing, commerce, and communication. In other words, this is an online platform that embraces different aspects of personal and commercial life. From a system point of view, um, a super app is a software platform that hosts and supports other applications such as mini apps, enabling their execution by using the platform's resources. In general, the user only has to or must log into the super app and enter a payment method. From there, the user doesn't have to register every time he or she accesses a new service. Some examples of super apps include Alipay, WeChat. This is a picture of WeChat, Tatanu, and Grab. In this image, we see a WeChat mobile interface where users can communicate using chats, they can transfer money, they can pay their bills, pay a coffee, do some shopping in different categories, and much more just by using one application, which is WeChat. In the previous slide, we mentioned a mini app. So, what is a mini app? From end user perspective, a mini app is just another function that he or she can use in or within the application. For example, we run. In this picture, we see the application we run, which is a mini app inside WeChat. This application or mini app allows users to keep track of their fitness evolution. Actually, a mini app or mini apps are small applications, commonly from 2 to 12 megabytes, that require a super app to run. The runtime of a mini app is a web view in the super app and not the underlying operating system. This characteristic makes mini apps cross-platform. It means that the same mini app can run in the same app, no matter if the super app runs on Android, iOS, or another operating system. Well, in this graph, we can see what we have described in previous slides. Mini apps, host apps, super apps, and an additional concept which is API. Well, first we have the host app or host application, which runs on an operating system in here and communicates with other applications such as mini apps using APIs or application programming interfaces. Let's use an example. Let's say we want to pay for an article, so we click the button buy now. What happens is that the super app is going to request the mini app market, this mini app, to validate the payment. We ask why? Just because the mini app has the logic, the development, to determine if a payment is valid or not. In fact, the Miniapp is going to return this message to the super app. It's going to say if the payment will succeed or not. It is important to mention that the super app has the database with all users' information and methods of payment. And mini apps just consume this data based on each request. So mini apps and super apps work together. In the next slides, we're going to, when we talk about super apps, we're going to be referring to the host app plus the mini apps all together as a super app. To expand on what has been mentioned before, a mini app, which is a full developed application, doesn't have an operating system. So the host application, the host app, provides the runtime environment to the mini app. To accomplish this, the mini app use services such as JavaScript executor and page renderer. The JavaScript executor is an interface that is used to execute JavaScript through Selenium WebDriver. In other words, the JS executor enables the WebDriver to interact with HTML elements in the browser. That's in general how a mini app works inside a host application, even though a mini app is a fully developed application. Resource management in mini apps or mini applications. So in this table, we have a summary of resources and the protection mechanism. This image was taken from the paper. In the first column, we have the resources. In the second column, we have the kind of protection or protection mechanism. There are four: PIVA, which are P stands for permission, I stands for isolation, V for vetting, and A for allow listing. In the next column, we have the permissions, if applicable. This is for subjects or objects, and the example APIs listed here. Besides, we have two groups. The first group is the front-end guarded resources, and the second group, the back-end guarded resources. All have different protection mechanisms. At a high level, as mentioned, the protection can be classified into permission-based, isolation-based, vetting-based, and allow list-based. In this table, it is described how resources are guarded based on where the resources are located, front-end or back-end. Front-end guarded resources, if we talk about front-end guarded resources, front-end resource can be protected by either the permission mechanism, P, from both the host application and the underlying operating system, or just isolation mechanism, I, from the operating system. To be more specific, the front end of a super app can use the permission mechanism, P, to check whether a given mini app has the corresponding permissions when accessing a protected resource. For instance, WeChat provides access for mini apps to both the operating system level resources, such as location, such as Bluetooth, and information collected from the users, such as addresses, mailing addresses. Meanwhile, the host application can also use the isolation mechanism provided by the operating system to protect resources. For example, the host application can create an isolated space for each Miniapp to prevent its files, let's say configuration files, data cache files, from being accessed by other unauthorized apps or mini-apps. From the backend gathered resources, well, the backend of the super app also needs to protect the resources from being accessed by unauthorized apps. To this end, the super app will first verify the authenticity and the corresponding permissions of the developers, and then grant them the access once they have passed the checks. For example, let's say an API request payment, this one, is not available to individual developers, but enterprise developers. To use such API, the enterprise developer needs to submit their business license to the super app provider for the vetting and can only use the APIs when they obtain the approval. Additionally, the super app backend can use allowing list, this column or subcolumn, to protect the network resources. Specifically, the Miniapp cannot access arbitrary web, as you can see, arbitrary web domains. As you can see, they only are allowed to access HTTPS, but only a list of domains that are trusted by the super apps. And that'll be all for this slide. We're going to talk about cross-Miniapp communication. In this slide, we have three images. The main image is this one, which is an illustration of cross-Miniapp communication. This image was taken from the paper also. And we have two more images, which are codes that are going to be used in the explanation. In the first image, we have three subjects, which are the sender Miniapp, the receiver Miniapp, and the host app, and overall they are super app. We have the backend, the front end, from the sender and the receiver, and each of the steps that are related to the communication that we're going to explain right now. Two Miniapps need to go through the three stages, as you can see: stage 1, stage 2 till here, and stage 3. And these three stages have 8 steps to achieve the cross communication. One, or the first stage, is the request creation and sending, where a sender Miniapp first creates a request. This Miniapp creates a request and invokes the communication API. Then, in the second stage, the channel establishment, where the host application receives the request. The host application, this is the host application, in this case is WeChat, and creates a shared memory-alike channel to save the request for the receiver Miniapp to consume. In the second and the third stage, the request receiving, where the receiver fetches the request from the channel. So to better explain these three stages, let's assume that a shopping Miniapp needs to communicate. This is the shopping Miniapp, needs to communicate with a payment Miniapp to complete a payment. So the shopping Miniapp, we have the shopping Miniapp, and the payment Miniapp, which will be the receiver, after the user presses the button purchase. Then, for the first stage, the shopping Miniapp gets the price and an order ID. Then it invokes the inter-Miniapp communication API. In this case, is navigate to mini program. To be more precise, this is step 1. Now the communication API has 3 parameters. As we can see here, as we see, the first parameter is the ID, Miniapp ID. In here, the second parameter is the path URL that the sender attempts to send the request. And the third parameter is the extra data, we can see here. Bear in mind that the extra data is a JSON object that contains the name of the request and the value of the request. For example, price and price. So in stage 2, which is channel establishment, when the cross-communication API is invoked from the Miniapp, it first notifies the host application on the ongoing communication request, which is the step 2. For example, when WeChat receives this request, it pushes the sender into a runtime stack, which maintains a few mini-apps that have been launched so far. This is step 3. Also, WeChat will release the resource of the mini-app located at the bottom of the stack if the mini-app stays inactive for more than 5 minutes. This is an important information to note. So after 5 minutes, WeChat is going to turn off the application. This is because the host application itself, in this case WeChat, is still a native application which has relatively limited resources when compared to an operating system such as Android. It means it can not allow a mini-app to continue to run and consume unlimited resources. The creation of shared memory alike space for the 2 mini-apps to communicate is simple. Facilitates to encapsulate the request into an object called app brand init config. App brand init config. And then it saves this object for future references in step 4. Now, subsequently, WeChat launches the receiver Miniapp based on the application ID specified by the sender, which is step 5. Finally, in stage 3, which is request receiving, the receiver Miniapp is launched, but first it invokes a callback function to fetch the request. The callback function will execute every time when the user interface launches in step 6. The callback function ultimately retrieves the safe app brand init config saved in step 4 and returns the request to the receiver running in the foreground in step 7. The receiver can also check the resource the receiver can also check the source of the request by comparing application ID with its expected to ensure that the request is from the expected Miniapp. In step 8, in the last image, here, we can see the receiver notifies the sender of the payment status, and at this moment, the receiver becomes the sender, and the original sender becomes the receiver. After analyzing the cross-Miniapp communication, we now are going to study the main purpose of this paper, which is the analysis of the cross-Miniapp request forgery attack. In number 1, we have the scope of the project. So, for proof of concept, this paper focuses on Miniapp scrolled from WeChat and Baidu, mainly for 2 reasons. First, because WeChat has more than 2 million Miniapps, and its user base has reached more than 1 million or billion users. Besides, WeChat is pioneering the Miniapp paradigm. The second reason is Baidu has more than 150,000 users, or 150,000 Miniapps, which are more than many other vendors. Number 2, based on how two Miniapps cross-communicate, we can see that the application ID, which is the app ID, is fundamental in cross-Miniapp communication, and it is used by the APIs. It works similarly to IP addresses in network communication, since an application ID is assigned and managed by the super apps. Theoretically, an attacker cannot pretend to be either the sender or the receiver. However, while an application ID cannot be forged by an attacker, a developer can make a mistake and put a Miniapp in danger. So it is the responsibility of the developer to ensure that the request consumed by the receiver Miniapp is from a trusted sender Miniapp. Any consumption of the request without an application ID check could lead to a cross-Miniapp request forgery attack, where an attacker can inject a forged request for a malicious purpose. And besides, the CMRF vulnerability to be impactful requires that the victim receiver Miniapp have access to protected resources such as Bluetooth or payment or location. So in number 3, we have the workflow of the CMRF attack. Whenever a receiver Miniapp does not check the application ID of the sender Miniapp, this Miniapp could be vulnerable to a cross-Miniapp request forgery attack. So to launch such an attack, the attacker can first statically analyze the format of the request by reverse engineering the victim Miniapps, then forge a request with a malicious payload with the same format, and finally inject the forged request to the victim to trick it into believing that the request is from a trusted sender and consequently perform a privilege operation. Similarly, once the request has been successfully injected, the receiver may also send back sensitive information to the original sender, and thus the sender can also steal the sensitive information from the victim receiver. So there could be at least 2 types of attack consequences, depending on the direction of the attack of the information: forward direction and backward direction. Next, I will explain each type of these attacks in detail. This slide, we're going to talk about the cross Miniapp request forgery attack in detail. We have the same three actors or subjects: the sender Miniapp, the host Miniapp, which is WeChat, and the receiver Miniapp. And it is divided into groups: the cross Miniapp request for data manipulation and the cross Miniapp request forgery for data stealing. Now, for the first part, data manipulation, an attacker can create a fake payment Miniapp and navigate back to the victim shopping Miniapp with a payment state of success. To be more specific, we assume that an attacker runs a shopping Miniapp on his smartphone. The attacker first selects a product, then presses the purchase button. Then the shopping Miniapp will invoke, this is the shopping Miniapp, will invoke the payment Miniapp, which will be the receiver, and wait for the payment to be completed. Everything worked fine up to this point. However, instead of finishing the normal payment procedure, the attacker terminates the payment Miniapp and runs the fake Miniapp on his development environment. Then uses the fake Miniapp to create a forged request, which contains the payment state of success, and send this to the victim receiver through the Navigate to Mini program from step 1. This is step 1. This can be easily achieved by waiting for more than 5 minutes, such the shopping Miniapp will be killed by the WeChat, which is the host app. Then the attacker can use the Navigate to Mini program to invoke the shopping Miniapp with a forged request. On the other hand, the shopping Miniapp will always use the callback function to retrieve or to receive the request from other Miniapp. The host application will launch the receiver Miniapp. In this example, the shopping Miniapp, based on the application ID specified by the attacker. This is the step 2. Since the shopping Miniapp does not check whether the application ID is from an intended Miniapp, and the request sent by the malicious Miniapp will be processed as usual in step 3. And therefore the attacker can achieve shopping for free attacks. This is the first part. Now, for the second part, which is data stealing, we part from the injection of this type of attack is built upon cross Miniapp request forgery for the injection of failed request, where the attacker goes a few steps further by receiving the request sent from the receiver. This time the receiver, in this example the payment Miniapp, is the victim. This is the payment Miniapp. Is the victim which leaks sensitive information, let's say a coupon, to the attacker, which should not be, this information should not be leaked, because it is supposed to be distributed only for the user who initiated the payment. We assume that the attacker has already used steps from 1 to 3. The attacker has completed these 3 steps via to Navigate to Miniapp, and now the attacker's Miniapp is switched offline. Since we assume that the receiver does not check the application ID, it will then believe that the sender is legitimate and will respond to the sender in future communications, such as step 4. The receiver finishes the request and subsequently sends the response, which contains the coupon, to the sender. By Navigate back to Mini program, which will notify the host application, which will further launch the original attacker's Miniapp. Finally, the attacker can use the callback function to on show or on launch to steal the sensitive information from the victim in step A. Now we talk about the cross Miniapp vulnerability detection. Since the lack of application ID checks is the root cause of the cross Miniapp request forgery vulnerability, the authors had to identify the missing checks in the Miniapp code in order to identify the vulnerability. So they presented the CMRF scanner, which is a JavaScript static analysis tool that uses the abstract syntax tree reconstructed from Miniapp code to scan for vulnerable apps. And you have to bear in mind that a Miniapp is subject to cross-Miniapp request forgery attacks when first it uses a cross-Miniapp channel or communication channel, and it does not check whether the request is from a trusted sender. It means the lack of ID check or application ID check. Therefore, the key idea for the CMRF scanner is that first to detect whether there is the use of the cross Miniapp request, and if so, this scanner then further detects whether there are missing application ID checks. So, the first point, to identify the use of the request across direct assignment is simple. If the value of the referrer info or referrer extra data is assigned to a specific variable, the scanner then records the variable and keeps track of whether the variable is assigned to other variables or not. For the second part, which is identifying the use of the request across function invocations, the authors proposed to store a call graph to record the caller with an index of the parameter of interest. The parameter is originally assigned from the referrer info extra data. In particular, for each function involving these parameters of interest, they scanned each of the parameters individually and recorded the analyzed result for future reference. Now, for detecting the missing checks, after having identified the use of cross-Miniapp request in part 1, it is necessary to see whether there are missing checks of application IDs. Fundamentally, if there is an application ID check, a receiver Miniapp must fetch the sender Miniapp's ID from the object referrer info application ID, which is set by the WeChat framework, and then compare with a string, a variable, or any array of application IDs, and so on. So for a specific Miniapp, as long as we have confirmed one path that involves the use of a request without checks, we conclude that the Miniapp is vulnerable to cross-Miniapp request forgery attacks. The conclusion. The authors have presented a novel cross-Miniapp request forgery attack, which is caused by the missing checks of the sender's Miniapp ID in a receiver's Miniapp. To understand how popular the Miniapps are vulnerable to their attacks, they developed a CMRF scanner, which has identified that 2.04% of WeChat Miniapps and 0.3% of Baidu Miniapp that have used the cross-Miniapp communication channel, from which almost 95% of the Miniapp of the WeChat mini apps and 99% of the Baidu mini apps are subject to cross mini app request forgery attacks. Among all these mini apps that do not validate the application ID, there are around 2008, which is 55% of the amount of WeChat mini apps that have the privileges to sensitive data and can lead to severe security consequences, such as shopping for free, promotion abuse, and device manipulation. Finally, according to the authors, the findings have been sent to the vendors. Um, then we have here the references that have been taken, different pictures and information. That'll be all. Thank you for your attention.